Hi, let's talk about electromagnetic radiation. Electromagnetic radiation is a wave-like property. It has alternating magnetic and electric fields. Now, we're not going to talk about the electric and magnetic fields too much, but the wave nature is important to us. What are the properties of waves? Well, we're all familiar with waves. We've been to the beach. We've seen waves come in from the ocean. What are the properties? Well, there's a speed that the wave moves. If you see a surfer and he catches a wave, the speed that the surfer moves riding the crest is the speed of the wave. We write that down on the board as a sine wave. That'll designate our wave-like property. And if it travels in a certain direction, we'll give that direction of travel and we'll give it speed. When we talk about electromagnetic radiation, it moves at the speed of light, as opposed to the speed of a surfer. So the speed is the speed of light. What other properties do waves have? Well, there's clearly the separation between the crests of the wave. If you see one surfer catch a wave and another surfer catch the wave right behind him, the separation between those two surfers as they approach the beach is the wavelength. And their speed will be equal, and their distance will stay about the same. Their distance between them, the wavelength. The length between the crests is given the symbol lambda and is the wavelength of the wave. Here's an example, 700 nanometer wavelength. That wavelength corresponds to a wavelength in the visible region of the electromagnetic spectrum, visible light. And I'll often use the term light and electromagnetic radiation interchangeably. 700 nanometers, when that electromagnetic radiation strikes our eye, appears reddish. Electromagnetic radiation with wavelength 400 nanometers appears bluish. So different wavelengths have different properties, and for some electromagnetic radiation, our eyes are sensitive to them. So we have different colors for different wavelengths. Another property of waves are the frequency. The frequency of the wave is how often a wave crest passed you. So if 3 wave crests passed you per second, the frequency would be 1/3, or 1/3 of a second. Now, we say reciprocal seconds, 1/3 seconds, we give that a special unit called hertz. 1/3 of a hertz is 1/3 seconds. The wavelength, the frequency, always multiply together to give you the speed. Product of the wavelength and the frequency is the speed, and for electromagnetic radiation, that's the speed of light, 3 × 10⁸ meters per second. We're going to talk about waves, electromagnetic radiation, and light all the time in this course, so we should be very familiar with the relationships between electromagnetic radiation, frequency, wavelengths, and speed. Electromagnetic radiation encompasses a broad range of wavelengths and frequencies, from astronomical proportions, 10⁸ meters, like Earth to Sun distances, down to tiny microscopic wavelengths, 10⁻⁻16 meters. The ranges have different names, basically historical names, describing the kinds of radiation in each band. So the long wavelengths, radio waves, microwaves slightly shorter in wavelength, still though in proportions we could resolve, few meters to a few centimeters. Infrared radiation now down below our range of resolving it. And visible, ultraviolet radiation, X-rays, and gamma rays. All these flavors of radiation are emitted by the sun, so during solar events, the Earth is bathed by all these kinds of radiation, and there's other sources of these radiation. Obviously, we can make microwaves and radio waves, infrared waves, and visible waves. We have flashlights, we have microwave ovens, we have heaters, we have radios. So all those things we're able to produce electromagnetic radiation. The visible spectrum, in particular, in between the infrared and ultraviolet, we're going to look at a lot. These are the wavelengths that our eyes are sensitive to, from 400 to 700 nanometers approximately. So blue, green, yellow, orange, and red light we can detect, and these wavelengths stimulate our eyes, and those signals travel to our brain, and we perceive different colors. The combination of all those colors altogether would give us white light. So from blue to red completely all at once, you would perceive white light. But you can take white light and break it back down into its component colors. You can do that with putting obstacles in the way, putting a grating in the way of the light, so the light of different wavelengths interacts differently with that grating or those obstacles. So long wavelengths are diffracted differently than short wavelengths, and you can spread out the wavelengths in space. And we can actually do that. Diffraction gratings are cheap and easy to make. There's actually some in these glasses here. What I'm going to do is I'm going to take this white light source, I'm going to turn that on, and we'll put on these diffraction glasses, and we'll be able to see when we look at the light, it resolved into blue, green, orange, red, its component colors. So this is a beautiful example of the electromagnetic spectrum, white light being resolved into its component wavelengths by a diffraction grating. We'll be talking a lot about wavelengths and visible light during this course, so this experiment with a diffraction grating showing separation of wavelengths is very useful for our understanding of light. When you talk about electromagnetic waves, the waves are properties of an electric and magnetic field. And they can be very long, like radio waves, or they can be very short, like gamma waves. But there's no sense that we have that can perceive them. We can't see them or smell them or touch them or understand the wave behavior. When we look at ocean waves, it's obvious that there is a wave property, and we can see their speed and their wavelengths and their frequencies. But with electromagnetic radiation, you can't. So it'd be nice to be able to demonstrate the wave property in an experiment. Well, with ocean waves, water waves, it's well known when those waves hit obstacles how they behave. So it'd be neat to arrange an experiment where an electromagnetic wave hit some obstacles and displayed those same kind of wave characteristics. So that's what we're going to do. So consider this. We're going to take a slit, a tiny little hole poked in a screen, and shine light through it, and then look far away at a wall or some other screen where that light hits and see what that looks like. So I think you understand this. This is like poking a hole in a pie plate and shining a flashlight through it onto a wall. You know what you would see. You'd see an image of the hole that you poked, and it'd be diffuse around the edges, and it'd be bright in the center. That's because the light is diffracting and spreading out around the edges of the hole you've poked. That's exactly what I've drawn here. I have a light passing through a hole, hitting a screen far away, and I've plotted the intensity distribution. Now this is monochromatic light, so only one wavelength involved. It's not like a flashlight, so it's more like a laser going through a slit. So what you have, though, is the same thing, a bright spot getting dim at the edges that I've plotted out here. So this intensity distribution is just like a probability distribution if it were particles. That is, let's say I shot bullets or BBs or something through a hole. Some of them would tick off the sides here, and they'd spread out, and they'd end out at the fringes, but a lot of them would go right through and hit directly across from the hole. So you'd have a high probability of a particle hitting directly across from the hole, and slightly lower probability as you move away from the hole. So let's look at another slit. We could do the same thing with light, a second slit, and have the same kind of experience where a lot of particles or a lot of waves or a lot of beams hit directly across from the slit. So two slits together is where it gets interesting. When waves interact, that's how we can tell they're waves. And you probably know this by looking at waves in the bathtub or waves on the beach. If there's something in the middle and waves hit them, there's a pattern that's predictable as those waves move away from the obstacle. So this is like an obstacle to light waves, and we'll talk about light in the visible spectrum so you can actually see it. So two slits, the light passes through them. What you might expect first is, well, you'd get a bright spot across from one slit and a bright spot across from the other slit. And it turns out for some wavelength and for some orientation of the slits, that's what you get. But if you arrange the slits appropriately, you get a very distinct pattern. Instead of two strong intensities across from slit A and slit B, what you actually see is a pattern of intensities, light and dark spots that aren't directly across from the slits. So you see bright spot, dark spot, bright spot, dark spot, bright spot, dark spot, alternating away from the center of the slits. The brightest spot is actually right between the slits. So that doesn't look like a particle-like property at all. Particles would never do this. If you shot your BBs or your ping pong balls or something macroscopic through these two holes, you would get a bright spot here and a high probability spot here. So this is a property only of waves. And how can we understand it? Well, it's actually pretty clear. If you think about it, a wave has to travel from the slits to the screen. And if a light has to travel from the slits to the screen, so here's a wave coming from each slit, hitting the center, notice that the distance that this wave has to travel and the distance that that wave has to travel will be the same. So two waves traveling in unison, the same distance, will be in phase. They will be either at a peak or a trough identically because they've traveled the same distance. Now, what about a dim spot up here? Well, if you think about a wave traveling from this slit and a wave traveling from this slit, this wave now has a longer distance to travel than this wave. So the one that has the farther path is going to be out of phase somewhat with the one that has the shorter path. So think about that. One wave travels up, down, up, down, up. The other one has a longer path. Up, down, up, down, up, down. So one arrives in an up phase, the other arrives in a down phase. And when you add those two intensities together, what you get is destructive interference. So the waves add to give zero intensity. It's actually really cool, and it's something you can see in the experiments that we'll show you later on. We'll shine a laser through a slit, and we'll actually show you this pattern of light and dark spots. This shows us that electromagnetic radiation is actually a wave. We're in the demo lab with Lonnie, where he set up a laser two-slit interference pattern. He set up a laser, a set of two closely spaced slits, and a screen where we can observe the alternating light and dark spots corresponding to constructive and destructive interference. So let's think about this interference pattern of light in terms of a chem quiz. So if you shine, say, green light and you obtain this two-slit interference pattern, how would that interference pattern change if you increase the wavelength lambda? So you go from, say, green light to red light, longer wavelength light. How will the interference pattern change? Will the pattern get more compact? Will it look about the same? Or will it get more dispersed? Think about that for a second and make a selection. Let's consider three possible explanations for the three answers. A, increased wavelength causes higher frequency spacing since wavelength and frequency are inversely proportional. Or B, the interference depends only on the spacing between the slits. So increasing the wavelength doesn't change anything and no change should occur. Or C, longer wavelength light causes destructive interference at larger intervals along the wall. Think about those three options and make another selection. When you change the wavelength in a two-slit experiment, what do you expect will happen? Well, what we know from our two-slit wave interference pattern is two slits cause a high intensity then low intensity because the paths are equal right between the two slits. But if you go to the first peak, say, then one wave has to travel farther than the other, and it's that extra distance that causes either constructive, a bright spot, or destructive, a dim spot, interference on the screen. So the larger the wavelength, the larger this spacing will be. That is, you have to move farther up the screen to make this path length long enough to get an extra half wavelength and give you constructive or destructive interference up the screen. So longer wavelength means a spreading out of the diffraction pattern on the screen, and the correct answer is C. So let's think about this interference pattern of light in terms of a chem quiz. So if you shine, say, green light and you obtain this two-slit interference pattern, how would that interference pattern change if you increase the wavelength lambda? So you go from, say, green light to red light, longer wavelength light. How will the interference pattern change? Will the pattern get more compact? Will it look about the same? Or will it get more dispersed? Think about that for a second and make a selection. Let's consider three possible explanations for the three answers. A, increased wavelength causes higher frequency spacing since wavelength and frequency are inversely proportional. Or B, the interference depends only on the spacing between the slits. So increasing the wavelength doesn't change anything and no change should occur. Or C, longer wavelength light causes destructive interference at larger intervals along the wall. Think about those three options and make another selection. When you change the wavelength in a two-slit experiment, what do you expect will happen? Well, what we know from our two-slit wave interference pattern is two slits cause a high intensity then low intensity because the paths are equal right between the two slits. But if you go to the first peak, say, then one wave has to travel farther than the other, and it's that extra distance that causes either constructive, a bright spot, or destructive, a dim spot, interference on the screen. So the larger the wavelength, the larger this spacing will be. That is, you have to move farther up the screen to make this path length long enough to get an extra half wavelength and give you constructive or destructive interference up the screen. So longer wavelength means a spreading out of the diffraction pattern on the screen, and the correct answer is C. When electromagnetic radiation interacts with matter, that radiation can be changed, or it can be emitted, or it can be absorbed in some way. This is a really important phenomenon in chemistry because we can't see atoms and molecules with our eyes. In fact, when you see on TV a scientist, they'll always have a lab coat, they'll have some safety glasses, and regardless of what kind of scientist is being portrayed, they'll always have a microscope. And when they want to tell you something about an atom or a molecule, they look through their microscope and they say, oh yeah, well that molecule's blue. That is just crazy. We can't see, there's no optical microscope that can resolve atoms and molecules. What we do is we have radiation of various wavelengths interact with atoms and molecules, and we deduce things about the molecules based on how those atoms and molecules interact with the radiation. So when radiation hits a molecule or atom or any kind of matter, many things can happen. It can be absorbed. Radiation can be emitted by excited atoms. The radiation can change from high frequency to low frequency radiation. There can be a reflection process. All kinds of different things that help us understand the matter. So let's talk about absorption and emission. It can happen in many different ways. You can have a continuous absorption. So you can have a continuous absorption of many wavelengths. So a band of wavelengths, different colors hitting you all at once. So for instance, when we see white light, that's all the colors mixed together coming at us. Or we could see a bluish red or yellowish orange, several different wavelengths coming at us at once. Or several different wavelengths could be absorbed at once. So absorption and emission happen in continuous, broad swaths of radiation. And this is actually why you perceive color. When white light, a combination of all the colors, hits an object, some of those colors can be absorbed. The colors that aren't absorbed pass through or are reflected back and hit your eyeballs. And the wavelengths that hit your eyeballs can be either red or blue or green. For instance, this screen looks blue because wavelengths of white light are hitting it, but only the blues are coming back and hitting your eyeballs. Now, absorption and emission can also be discrete or line-based. That is, specific wavelengths are absorbed. So you could broadcast or have a lot of radiation hitting an object in a broad band, but only certain wavelengths are absorbed and removed from the spectrum. That's how that would look. Now, you could also have that in emission. You could have only certain wavelengths emitted from an excited atom or molecule or excited matter. Again, this would help you perceive color. If a blue and a green and a yellow wavelength were emitted from an object, that object would appear greenish blue. So we can actually look at absorption and emission from atoms. And I can show you a continuous emission spectrum. It's actually several lines being emitted at once from atoms. So let's look at that. I'll put on my safety glasses so we can do an experiment safely here on the desktop. And I'm going to bring in a series of tubes filled with gas. Now, there's various different gases here, and I can excite these gases with an electric current, and then they'll emit electromagnetic radiation back to you in the visible region so you can see it. And there'll actually be some that aren't in the visible region, but we can't see them, so it doesn't matter. What I'm going to do, I'll take an electric current here, a little stimulator, and stimulate these atoms of gas, and you should see light, visible radiation coming out of the tubes. So there it is. Stimulated emission from excited gases in the visible range. That's a really interesting experiment, and it shows when a line spectrum is emitted, and there's several lines at once, you'll see kind of a bluish green or a purplish color. Let's look at absorption. Here I have some colored solutions. And why are these solutions colored? Well, white light is hitting them. And when the white light hits them, several wavelengths are absorbed, other wavelengths pass directly through and hit you in the eyeball. So red wavelengths pass through and hit you in the eyeball for this solution, and blue wavelengths, other colors absorbed, but blue passes through and hits you in the eyeballs. So we're saying all colors but red are absorbed by this. Can I prove that in a different way? Well, here's a red pen laser. If I shine this red pen laser onto my hand, I think you can see it there. Now, what I'm going to do is I'm going to shine this red pen laser through the red solution, and I'm telling you, and I think you probably agree with me, that the red should pass right through because this solution does not absorb red. Red's hitting your eyeballs now. So this red pen laser, now passing through the solution, still hits my hand. But I told you this blue solution, it must be absorbing reds, or you'd be seeing some red. So I should be able to take my red pen laser, here it is just on my hand again, and pass it through this blue solution and have the red pen laser absorbed. So let's do that. Here it is hitting just my hand, and I'm going to move back till I go through the solution, and you can see the red is now absorbed by that blue solution. That's a beautiful demonstration of a discrete, a single wavelength, a line absorption by a blue solution. That's how colors work. Absorption and emission we're going to talk about a lot in this course because they help us understand matter. So let's think about this interference pattern of light in terms of a chem quiz. So if you shine, say, green light and you obtain this two-slit interference pattern, how would that interference pattern change if you increase the wavelength lambda? So you go from, say, green light to red light, longer wavelength light. How will the interference pattern change? Will the pattern get more compact? Will it look about the same? Or will it get more dispersed? Think about that for a second and make a selection. Let's consider three possible explanations for the three answers. A, increased wavelength causes higher frequency spacing since wavelength and frequency are inversely proportional. Or B, the interference depends only on the spacing between the slits, so increasing the wavelength doesn't change anything and no change should occur. Or C, longer wavelength light causes destructor interference at larger intervals along the wall. Think about those three options and make another selection. When you change the wavelength in a two-slit experiment, what do you expect will happen? Well, what we know from our two-slit wave interference pattern is two slits cause a high intensity then low intensity because the paths are equal right between the two slits. But if you go to the first peak, say, then one wave has to travel farther than the other, and it's that extra distance that causes either constructive, a bright spot, or destructive, a dim spot, interference on the screen. So the larger the wavelength, the larger this spacing will be. That is, you have to move farther up the screen to make this path length long enough to get an extra half wavelength and give you constructive or destructive interference up the screen. So longer wavelength means a spreading out of the diffraction pattern on the screen, and the correct answer is C. We're in the demo lab with Lonnie, where he set up an experiment to show absorbance of colored solutions. He's broken up white light into its component colors, and when he places a red solution in the path of the white light, notice that red is transmitted, but green and blue are absorbed. Now, a yellow solution. When the yellow solution is placed in the path of the white light, we'll see that the blue is strongly absorbed, and a combination of red and green is what causes the yellow color. Finally, we have a blue solution. The blue solution should absorb the red and the green and transmit the blue. So here we see the origin of colors. Colors are absorbed and transmitted, resulting in the colors that we observe. Thank you, Lonnie. So let's talk about absorption of light in terms of a chem quiz. If you have an object that has an absorption spectrum that looks like this, what color is that object? Is it blue, green, or red? Think about that for a minute and make a selection. Let's consider an argument for each of the possible answers. Answer A, blue light passes through the filter, so the object will appear blue. Answer B, a filter that absorbs red and passes blue will make an object appear green, or red light is absorbed by the filter, so the object will appear red. Think about those three possible solutions for a minute and make another selection. An object that has an absorption spectrum that looks like this is absorbing strongly in the reds and the yellows and passing wavelengths in the blue. So blue wavelengths will pass through, strike your eye, and this object will appear blue. Let's look at a couple filters and how they'll affect a blue object. So three possible filters put in front of a blue object. Which one of them would make the object appear black? Think about that for a minute and make a selection. Let's look at some possible explanations for each option. Filter 1 passes blue light and violet light, which combine to form black. Or option B, filter 2 absorbs the blue light from the blue object, making it appear black. Or filter 3 removes violet and ultraviolet light, making the object appear black. Think about those and make another selection. So we've got a blue object. We're going to put filters between the blue object and us, and we're going to see what we see. So a blue object, wavelengths of blue light are being emitted from that object. That's why it appears blue. How do we make it appear black? Well, we have to remove that remaining blue wavelength, essentially removing all the wavelengths from that object, so none hit our eye, and we have a black object. So we need to find a filter that absorbs strongly in the blue, and that is filter number 2. Correct answer here, B. We all know glass is transparent. So let's look at absorption over a broader range of the electromagnetic spectrum. Transparent glass should have an absorption spectrum that looks like either 1, 2, or 3. Think about that for a minute and make a selection. Let's look at an argument for each of the answers. A, transparent glass passes all visible wavelength and only absorbs above the UV. Or B, transparent glass must absorb some light in the visible region. Or C, transparent glass must absorb the entire visible region. Think about those alternatives and make another selection. The absorption spectrum of transparent glass is what we're talking about. And we're talking about a rather broad region of the electromagnetic spectrum, from ultraviolet wavelengths down to infrared wavelengths. And I've overlaid the common visible colored wavelengths in the center. So let's look at those 3 absorption spectra. Number 1 absorbs strongly in the ultraviolet. Number 2 absorbs strongly in the ultraviolet and some visible wavelengths. And option 3 absorbs ultraviolet, visible wavelengths, looks like most of them, and terminates somewhere in the IR. So it also absorbs a little bit of infrared wavelengths as well. But in order for the glass to be transparent, all visible wavelengths must pass through. Transparent glass will pass white light directly through it. You can see all colors through transparent glass. So all colors must pass through. So we have to choose one that has no absorption spectra in the visible range. That is option 1. So the correct answer here is A. Let's do a calculation with electromagnetic radiation, the properties of wavelength and frequency. What frequency and designation of radiation with wavelength 8.83 picometers is emitted from technetium-99 during its nuclear decay? So we understand a wavelength, 8.83 picometers, we can change that into a frequency knowing that the waves travel at the speed of light c. So the product of the wavelength and the frequency is the speed. We can solve for the frequency. The frequency is the speed over the wavelength, and just simply plug those 2 numbers in. 8.83, and now I've written 10 to the minus 12th meters because my speed of light it has the units of meters per second, so I want all my units to be the same. I can do that division. 3.4 times 10 to the 19th reciprocal seconds, or 3.4 times 10 to the 19th hertz. So very, very, very high frequency, very short wavelength as we'd expect. What region of the electromagnetic spectrum does that correspond to? Well, this wavelength in picometers firmly in the gamma wave region of the spectrum. So we have gamma waves emitted from technetium-99 during its nuclear decay. Let's do a calculation with electromagnetic radiation, the properties of wavelength and frequency. What frequency and designation of radiation with wavelength 8.83 picometers is emitted from technetium-99 during its nuclear decay? So we understand a wavelength, 8.83 picometers, we can change that into a frequency knowing that the waves travel at the speed of light c. So the product of the wavelength and the frequency is the speed. We can solve for the frequency. The frequency is the speed over the wavelength, and just simply plug those 2 numbers in. 8.83, and now I've written 10 to the minus 12th meters because my speed of light it has the units of meters per second, so I want all my units to be the same. I can do that division, 3.4 times 10 to the 19th reciprocal seconds, or 3.4 times 10 to the 19th hertz. So very, very, very high frequency, very short wavelength as we'd expect. What region of the electromagnetic spectrum does that correspond to? Well, this wavelength in picometers firmly in the gamma wave region of the spectrum. So we have gamma waves emitted from technetium-99 during its nuclear decay. Electromagnetic radiation is composed of wavelengths from very, very long to very, very short. We've talked about the relationship between the wavelength, the frequency, and the speed of electromagnetic radiation. In fact, the product of the wavelength and the frequency is the speed. For electromagnetic radiation, light, speed is fixed at the speed of light. So if the wavelength increases, the frequency has to decrease. They're inversely proportional. And you can see I have wavelength increasing here and frequency increasing here. The visible region in particular we're going to talk a lot about because we can perceive the length of the radiation by the color. So we can make that easy connection between a wave and its length by the color that we see. Long wavelengths in the visible region are red, intermediate wavelengths going down from yellow to orange to green to blue, indigo, and violet, from long to short wavelengths. In fact, this kind of spells a guy's name, Roy G. Biv, from long to short wavelengths. I often write that down, and I can remember the colors of the rainbow. Now, there's more properties to electromagnetic radiation and waves in general. For instance, the intensity. We haven't touched on that yet. You can think of the intensity of waves in the ocean as their height as they come in to the shore. A big wave would be an intense wave, a tall wave, an intense wave. How do we do that for our electromagnetic radiation? Well, let's talk about intensity more as we go through this talk. Now, the intensity of light, or electromagnetic radiation, may be more of an intuitive property. Let's look at it this way. If you have an intensity originally of I0, you pass it through a filter, and you get an intensity of half that, I0 over 2. What would the intensity be if you put an additional column in the path? So I0 going through a pair of identical filters. Would that reduce the intensity down to a quarter, an eighth, or 0 of the original intensity? Think about that for a minute and make a selection. Let's consider an argument for each of the possible answers. A second filter reduces the intensity by 1/2 again, so you have a quarter of the original intensity. B, the second filter has twice the effect, reducing the intensity by a factor of 4, so 1/8 the original. Or option C, the first filter removes half the intensity, so the second removes the remaining intensity, giving you 0 intensity. Think about those three possibilities and make a selection. So we've been talking about intensity, the brightness of light, in terms of attenuating it or reducing it with a filter. So an original intensity reduced to half the brightness by a single filter, what would be the effect of an identical filter put in the path again? Well, if the first filter reduces it by 1/2, so it's half as bright here, a second filter would make this half as bright. So you'd go from half the original intensity to a quarter of the original intensity after 2 filters. So the correct answer here is A, 1/4 the original intensity. The intensity of light, or its brightness, can be considered in a thought experiment, just like we did with matter. We said, if I take a chunk of carbon, solid matter, and I cut it in half, and then in half again, and again, and again, and continue cutting it in half till I get the tiniest piece of matter that still has the properties of carbon, that tiniest particle would be an atom. Can we do that with light intensity? Can we take a bright light, and bring in filters that reduce the intensity by a factor of 2, cut the light intensity in half, again and again and again and again and again. Well, of course we can do the experiment. What happens? Well, if you were watching this experiment, the light would get dimmer as each filter was added. And the light would eventually dim completely. But then something interesting would happen. You would see individual flashes of light. It turns out your eyes are accustomed to the smallest unit of light, individual pulses. These individual pulses like particles of light. Just like chopping matter up until you get the smallest particle and atom, you can reduce light intensity till you get the smallest particle of light. Indeed, we call these particles of light, these tiny flashes, we call them photons. And these photons carry the smallest amount of energy of light. A photon is what we call it. And the energy of the photon is given by h, Planck's constant, times the frequency of the light. So the frequency of the light times Planck's constant gives you the energy of the photon, one of the most important equations in this class. In fact, if you take nothing else home from Chem 1, take home the fact that the energy of photons is given by Planck's constant times their frequency. Planck's constant, a very small number, 6.62 times 10 to the minus 34th joules seconds. That tells you this is an incredibly tiny amount of energy. But our eyes can detect it. That's the interesting thing. If you do this experiment in a dark room where your eyes are acclimated to the dark, your pupils wide open, you can actually reduce intensity till you see the individual flashes of photons. It's a fascinating experiment to do. Now, visual perception has been quantitated for a long time. We've said that the limits of human perception are a candle on a clear dark night at 30 miles away. That's when the intensity is at the level of individual photons hitting your eye. So light has a particle nature just like matter has a particle nature. Now, we can detect that particle nature of electromagnetic radiation of all forms. This we did a thought experiment on visible light. We can take gamma waves. Remember that high frequency, and now we know high energy light. Well, here's a radioactive source. This is radioactive cesium-137. It emits gamma waves when it decays. It's not particularly dangerous to be around this kind of radiation. I'm going to turn on a detector for that radiation, something you've probably heard of, Geiger counters. You see these all the time on the television when you're talking about radiation. If I turn this on, when it detects photons of gamma radiation, it'll bleep. And you can hear it bleeping right now. The reason is there's cosmic radiation around us. Gamma waves are hitting us all the time. And the little packets are detectable by this device. Now, there's a lot of gamma waves. This is a bright gamma source. So this is intense radiation compared to the background radiation. And let's bring that in front of the detector. And now watch, I'm going to bring the source closer and closer. And listen. You can see how bright this is. There, now 10 or 15 photons every few seconds. And now we're going to get into almost continuous bombardment of photons. They're hitting so fast. Brighter and brighter, more intense as you bring the source closer to the counter. Each one of those little blips, an individual photon, an individual particle, an individual packet of light. So we've learned that light has a particle nature. There's a wave property associated with light and electromagnetic radiation, and also a particle nature, packets of energy being carried along the wave. A brilliant experiment that demonstrates that property is the photoelectric effect. And here's how it works. You take a piece of metal. Now, metal is an array of metal atoms, and each of those atoms holds on rather loosely to its outer electrons. That's why the metal conducts electricity. Those electrons are rather free to move about the surface. Now, if you shine light on that surface, what happens? Well, you can shine light of certain wavelengths. Here we'll bring in a rather long wavelength, a red photon. And when a red beam of light hits that, you'll find for many metals, nothing happens. And even if you make the light very bright, very intense, nothing happens. If you bring in a green beam of light, this now has higher energy photons, shorter wavelength, higher energy. What you find is that electrons are indeed ejected. It's as if photons are striking electrons and kicking them off the metal. You bring in a more intense green light, and you get more electrons. They don't go away faster. You just get more electrons with a brighter light, all with the same kinetic energy. You bring in blue light, now higher energy photons, even a shorter wavelength, and you find that electrons with even higher kinetic energy are ejected. And again, the same correlation with brightness. If you make the light brighter, you get more electrons per second released. So it's as if the electrons are caught in a well, and there's an energy barrier that holds the electrons next to the metal. You have to overcome that energy barrier to eject the electron and release it from the metal. We'll designate this threshold energy, or this well depth, with the symbol phi. So red light, the photons of red light don't have enough energy to even get out of the well. So it doesn't matter if there's more of them, if there's more intense light, more photons per second, still none of the electrons leave the well. Electrons or photons in the green region, so shorter wavelength, have enough energy to overcome this binding energy of the electron being held to the metal, and a little bit of kinetic energy. More energy still in blue photons ejects electrons with even more kinetic energy. So it's as if the photons of light are coming in and jostling electrons. Like I'm holding on to this tennis ball. Photons are coming in and jostling them. The higher energy the photon, the more jostling occurs, until you get to a photon that can actually, higher energy now, break the photon free of the metal. Can I have my tennis ball back? If you go to higher and higher energies, bigger and bigger photons, in this case blue light, you'll eject the electron with more kinetic energy. Now brightness doesn't matter. We said, well, brightness is just more photons per second. That's just pep, 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 pep. But not enough energy, one photon per electron, to eject any single electron. But big photons, high energy, blue light, say, comes in and slams that metal and really sends the electron flying. Oh. Sorry, guys. High energy is what we have. So we can actually plot it. We can plot the kinetic energy of the electron versus the frequency of the light that we shine on the metal. And we know up to a certain frequency, no electrons are ejected. And then you'll reach that threshold, you'll just overcome the binding energy holding the electron to the metal, and you'll start to eject the electrons. Then higher frequency light just gives you more kinetic energy in the electron. The energy of the photon, we know, is h nu. So we can write the kinetic energy that the electron has is the energy that the photon comes in at minus this binding energy. So all the excess energy of the photon goes into kinetic energy. So you can write both energies in terms of photons, and you can realize there's a minimum photon energy required to eject the electron from the metal. If you look at different metals have different threshold frequencies. For instance, you could have a metal that's described by a blue photon as the minimum photon that ejects an electron. And higher energy photons give electrons with more kinetic energy. So this problem, the photoelectric effect, helps us understand the particle nature of light. And it's actually Albert Einstein, a genius who looked at this problem. Scientists, before the photoelectric effect was understood and the particle nature of light was understood, were taking their metals, shining lights, and increasing the intensity, figuring I should knock off more electrons. But increasing the intensity, very bright light, didn't do anything. And when you could eject electron, increasing the intensity didn't increase the energy of the electrons. You just got more electrons coming off with the same energy. Well, it takes a genius often to look at a very troubling problem and see it in a whole new light. And that's what Einstein did. He said, well, that looks like the light's behaving like particles. It looks like little bits of light are coming in. So a bright light is just lots of bits. But they all have the same energy. So those lots of bits eject lots of electrons, each electron with the same energy. So the photoelectric effect and Albert Einstein have helped us understand the particle nature of light. We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelengths still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great demonstration. Let's talk about the photoelectric effect in terms of a chem quiz. If we shine a beam of light on a certain metal, it has no effect. The question I have for you is, what change in that beam should I make in my best hope to eject electrons? Should I increase the intensity of the light, decrease the wavelength of the light, or increase the energy of the light? Think about that for a minute and make a selection. Consider these possible arguments for each of the answers. Answer A, increased intensity means more photons strike electrons, increasing the electron kinetic energy. B, decreasing the wavelength increases the photon energy, which increases the kinetic energy imparted to the electrons. Or C, increase in the energy of the photons increases the kinetic energy imparted to the electrons. Consider those arguments and make your selection again. When you think about the photoelectric effect, you think about the energy, the wavelength, the frequency, all those are related, of the photon striking the metal. If you have a photon that won't eject an electron, what do you need? You need photons with more energy. You have to increase the energy of the photon. Increasing the number of photons won't do. You'll just strike a lot of electrons with a little bit of energy. That doesn't help you. So increasing the intensity is not going to work. You want more energy in each photon. The energy of photons is h nu, or hc over lambda. So it's inversely proportional to the wavelength, directly proportional to the frequency. So if you want to increase the energy, you should decrease the wavelength. So increased energy photons will work, answer C, but if you are clever, you also noticed a decreased wavelength in the photon will also work, because that will increase the energy. So here you could have answered B or C, and you would have got an electron ejected from that metal. Let's look at the photoelectric effect again. which combination of a photon striking a metal ejects an electron with the highest kinetic energy? So I have two metals represented and several different photon energies. So is it a yellow photon striking metal 1, a green photon striking metal 1, or a blue photon striking metal number 2? Think about that for a second and make a selection. Let's consider an argument for each of the three answers. Yellow light is high energy with a lower threshold metal, so it'll give the highest kinetic energy electron. Or B, green light is higher energy than yellow light and is striking the same metal. Blue is striking a higher threshold metal, so green on metal 1 should be the highest. Or blue light is the highest energy of all three photons, so it should eject electrons with the highest kinetic energy. Think about those three for a minute and make another selection. So which combination of photon and metal gives the electron with the highest kinetic energy? Let's look at all three. Yellow light striking metal 1, well, I've kind of outlined about where the frequencies are, but of course a single frequency can't encompass the whole band of green and the whole band of blues. So the largest yellow is somewhere below the green. That's all we know. So it's somewhere in here. So the largest possible yellow photon striking metal 1 would give a kinetic energy here. What about green striking metal 1? Well, we know the green photon will be higher energy than the yellow photon. Striking metal 1 will give a higher kinetic energy. What about blue photon striking metal 2? Well, here's the blue region, so somewhere in here we'll have a photon, but it'll strike this metal with the higher threshold energy. So you can read the kinetic energy right off the plot. So a blue photon, even though it's the highest energy, is striking a higher threshold metal, resulting in lower kinetic energy photoelectrons. So green light on metal 1 will give the highest energy electrons ejected from this metal system. Light has both the properties of a wave and the properties of a particle. It's a wave and a particle at the same time. There's a duality to the wave-particle relationship. Wave properties, like wavelength and frequency and speed, somehow must be related to particle properties. Particle properties that are moving, the most important property is the momentum. Its mass times its velocity. So how do we reconcile the two? Well, light, photons of light, carry no mass, so how can they carry momentum? Well, they carry a relativistic momentum. Their energy is given by h nu, or hc over lambda. The energy can also be expressed by the mc squared relativistic energy, but we can cast that in terms of a relativistic momentum, so a single quantity and the speed. So using those two relationships, we can derive that the momentum is Planck's constant divided by the wavelength. So here's a single relationship that shows particle and wave nature in the same relationship. So particle and waves, a duality. The wavelength is related to the momentum is related to the wavelength for light. Planck's constant unites the two, 6.62 times 10 to the minus 34th joules seconds. Wave, particle, acting together, sometimes the properties of the particle exert themselves, sometimes the properties of the wave exert themselves. They both exist together all the time, particle and wave nature of light. We've talked about photons as the smallest particle of light. And we've said when you get down to the photon level, if you split that photon further, it loses the properties of that light. And indeed, splitting a blue photon into other photons is possible, but it no longer has the properties of the blue light that it originally had. It's the smallest particle of blue light that you could have, but splitting it is still possible. So let's talk about that. A photon at 400 nanometers is split into two. One of the photons that comes out is at 1200 nanometers. What is the wavelength of the other photon? So let's consider that. Is it A, 200 nanometers, B, 600, or C, 800 nanometers? What is that other photon? Think about that for a minute and make your selection. Let's consider an argument for each of the answers. A, splitting a photon must reduce the wavelength, and 200 is the only smaller wavelength. B, energy is conserved, and it's inversely proportional to wavelength. So 1 over 400 equals 1 over 600 plus 1 over 1200. Or C, the sum of the wavelengths must be conserved and add to the longest wavelength. So 1200 is 400 plus 800. Consider those three arguments and make a selection again. When we split a photon into two other photons, the total energy that we start with can't be lost. So energy will be conserved. So the two smaller photon energies must add to the original photon energy. And photon energies add as the inverse of the wavelength. So indeed, hc over 400 must equal hc over 1200 plus the other photon emitted, and that must be hc over 600. So indeed, two lower energy photons add to give the high energy photon, and the correct answer here is B, a 600 nanometer photon is split along with a 1200 nanometer photon when you split that 400 nanometer photon. Let's do a calculation involving the photoelectric effect, ejected photoelectrons and photons of a certain energy hitting a metal. We'll take the question, what wavelength of radiation must be used to eject electrons with a velocity given from chromium metal with a work function that's given? So this work function for chromium metal, 4.37 electron volts, is how strongly chromium holds on to its electrons. So we have to say, well, what is the photoelectric effect? The photoelectric effect, we have to balance the energies. Remember, the photoelectric effect has the kinetic energy of the electron is the photon energy minus the work function for the metal. So the metal holds on to the electron, but if we bring in a high enough energy photon, we can eject an electron with a certain kinetic energy. So that's what we have to find. Let's look at what wavelength will work for this problem, and what we'll do is we'll balance the energies involved with a common unit. And the units we always use are kilograms, meters, seconds, and joules, the SI units. Now, we do that to keep all the things we multiply together consistent unit-wise. We're dimensionally consistent. We always use kilograms for mass, so don't just put your masses into your equations with grams or pounds or some random mass unit. If you come across a mass, convert it to kilograms. If you come across a distance, a length, convert that to meters. A time, seconds. An energy, joules. That'll keep your energies, your units consistent and allow you to do the calculations correctly. So again, the kinetic energy of the electron is the energy of the photon minus the work function of the metal. We can calculate the kinetic energy of the electron. We're going to have to look up its mass and use the velocity that we've been given. So we'll use kilograms for its mass, meters for the length, per second for the velocity. Meters per second squared. Mass, velocity squared. That's going to be an energy, a kinetic energy. So this will be joules. In fact, that's how I remember the SI units of joules. I remember kinetic energy is a joule, and kinetic energy is mass times velocity squared. So it's kilogram, meter squared per second squared. So this has been pretty straightforward. We'll look up the mass of an electron, express it in kilograms, express our velocity, was given in kilometers per second, but I'm going to convert it to meters per second to keep the units the same. Square that. That's relatively straightforward. 11.16 joules times 10 to the minus 19 tiny, tiny, tiny number of joules. Of course, it's an electron. So with that kinetic energy, we can continue to balance our energy. We know the kinetic energy is 11.16 times 10 to the minus 19th joules. The work function we've been given, that's 4.37 electron volts. Now, electron volts in a unit of energy. It's the kinetic energy that an electron gains as you accelerate it across a potential of 1 volt. We don't have to know that, but it is nice to know that I can convert joules to electron volts with a simple conversion factor I can look up in any textbook. 1.61 times 10 to the minus 19th joules per electron volt. So we can do that product. So the work function in terms of joules, 7.04 times 10 to the minus 19th joules. So we'll rearrange now and solve for the energy of the photon. The energy of the photon is the kinetic energy of the electron plus the work function. That has to equal 11.16 times 10 to the minus 19th joules. And we're going to add on that work function, 7.04 times 10 to the minus 19th joules. We can express the photon energy in terms of its wavelength as well as its frequency. And that has to equal the sum of these two, or 18.20 times 10 to the minus 19th joules. Of course, we can solve for the wavelength now. That's just hc over 18.20 times 10 to the minus 19th joules. And we can do that math. This number, plug in Planck's constant and the speed of light in joules per second and meters per second. And then we'll notice that the units of joules will cancel out, and the units of seconds will cancel out, and leave us units of meters. And that's what we want. It's always good to check. Do the units that we have left make sense for the quantity that we're solving for? We're solving for a wavelength, a length. Do I have meters? In this case, I do. So I have, doing the math, 109 times 10 to the minus 19th meters. Excuse me, 109 times 10 to the minus 9th meters. That's a nanometer. 109 nanometers is, as we recall, in the UV, the ultraviolet region. We know visible went from 700 down to 400 nanometers. Below 400 nanometers, at higher energy, are the ultraviolet photons. So an ultraviolet photon is required to eject an electron from chromium metal. So we understand light as behaving like a wave, like on the ocean, with a wavelength and a speed, but also like a particle, a little packet of energy. And the energy amount is h times nu, Planck's constant times the frequency of the light. Now, a particle has momentum. And we've seen the momentum of the particle, that photon, can cause an electron to be ejected from the metal. We saw in the photoelectric effect an incoming photon ejecting electrons from a metal. So how does that particle nature and wave nature reconcile themselves? Well, let's talk about that. The light-wave-particle duality. If light behaves like a wave, we understand, with a wavelength and a frequency and a speed, we can write down its energy as a particle as h times nu and h times c over lambda, using the wave properties to write the energy in two different ways. Now, the wave particle, the light particle that we call a photon, has a momentum. We've seen it can transfer momentum from the photon to the electron, but the momentum is, we often associate with mass. But the photon has no mass. The photon is a particle, and it's massless, moving at the speed of light. But we can say the energy of the particle, use Einstein's equation for relativistic particles moving near the speed of light, mc squared is the energy. Now we have two expressions for the energy of the photon and the relativistic energy mc squared. Mass times velocity, mass times the speed of light c in this case for a photon, can be written as the momentum times c. So the momentum is m times c times another c gives you mc squared. So these expressions for the energy equivalent to these expressions to the energy. So what we can do is write the momentum then in terms of these two energies, and we'll find the momentum is the Planck's constant divided by the wavelength. So a simple relationship between the momentum and the wavelength, the particle characteristic, momentum, and the wave characteristic, the wavelength, both expressed at the same time. Waves and particles acting the way they choose. Sometimes light will behave like a wave, sometimes it behaves like a particle. There's a duality between them expressed by this beautiful relationship between the wavelength and the momentum. Planck's constant, again, an extremely small number, is the proportionality constant between the momentum and the wavelength. So waves, particles, light, we have to think of them all at the same time. Light behaved like a wave and a particle. And we came up with a beautiful relationship between the particle nature, its momentum, and the wave nature, the wavelength. It'd be interesting to say, well, let's go back to particles. Could it be possible that particles have wave nature? We were a little surprised when we saw the wave-like property, light, have a particle nature. Is the dichotomy going to continue? Is a particle able to have a wave-like property? Well, we would define it in the same kind of way. We would say a particle has a momentum, and electrons, for instance, they can move, and they'll be moving at a certain velocity. You take the product and their mass and velocity, that's a momentum. A wave would have a wavelength. If we say, well, we had this relationship that had wavelength and momentum in it to relate for light the duality between the particle and wave nature. The same thing can be applied to matter. And this is actually a very fascinating concept. How can a particle, like an electron, also behave like a wave? I think you can kind of buy the light argument. Light behaves like a wave, and we saw it with diffraction and interference. We had one wave going like this and one wave going like this. When they came together and they added constructively, you got a bright spot. When they added destructively, you got a dark spot. And that was very wave-like. We saw their particle-like nature of light in the photoelectric effect. Particles for matter, that's obvious. Here's a particle of matter. There's particles of matter, atoms, electrons, fundamental particles. But will they also have a wavelength? Will there be a duality here? It turns out there is. It's one of the most fascinating properties of nature that very tiny particles have a wavelength associated with them. We associate the wavelength through the same relationship we used for light. We call this the de Broglie relationship, the momentum and the wavelength related. For particles, we're going to use the intensity of their wave squared as the probability of the particle being found in that region. We'll talk about squaring the wave function of matter to get the probability of whether that matter actually exists there. So waves and particles, two totally dissimilar things, but the particle and wave duality works for matter. So how can we prove it? Well, remember how we proved that light behaved like a wave? We shined the wave through some obstacles. We got this diffraction and interference pattern, bright spots and light spots on the screen. That said, oh, that's a wave-like property. Matter, we understand as a particle already. Can we just demonstrate its wave-like nature? Well, it turns out you can. You can take electrons and you can shine electrons at little obstacles. In this case, you use the spacing between the layers in a crystal. You shine an electron at that, and that gives you diffraction and interference. And if you shine that on a screen, like you did with the light, you find that there's places on the screen that the electrons hit, and you get bright spots, lots of electrons hitting in certain spots, and places on the screen where the light does not hit. The electrons pass through their grating, their crystal. It's very likely they'll hit at some spots. It's unlikely to zero probability that they'll hit at other spots. And that's very strange. If you take just a BB gun or a machine gun and you shoot it through an obstacle, There's no place beyond the slits where the bullets cannot hit. There's no excluded particles. There's no excluded space where you cannot hit there. With electrons, it's a different story. You pass through that grating, you pass through that crystal, and there are places where the electron is forbidden to hit. There's electrons interfering with each other. You're allowed to hit here, you're not allowed to hit here. There's dark and light spots that detect the electrons, high intensity, high probability of finding electron in certain spots, low probability dark spots in other spots on the screen. Electrons behaving as if they're interfering with each other, just like they have a wave property. Fantastic property of electrons that we can actually demonstrate. So it's easy to show electrons give you a probability distribution. You'll have electrons going through their crystal grating, likely very strongly to hit at some spots, unlikely to hit at other spots. So matter, electrons in particular, displaying wave-like properties. Particles can behave like waves. They can have a wave-like property. And the wave-like property, wavelength, is given by the de Broglie relationship. A particle that has a momentum, a mass, and a velocity will have a wavelength given by the momentum, Planck's constant, divided by that wavelength. Let's look at some concrete examples to see actual particles and what their de Broglie wavelength would be. Here's a list of particles and their de Broglie wavelengths. A photon, now that's a particle of light. That obviously has a wavelength that we've talked about. A yellow photon, its de Broglie wavelength, 600 nanometers. How about an electron moving at 10 to the 5th meters per second? So an electron just zipping along in space. You can use the de Broglie relationship to find a de Broglie wavelength of around 6 nanometers for that electron. A sodium atom at 800 or 80 Kelvin, that's a temperature, that determines the average speed in the system. The average speed of those particles around 300 meters per second. We know they're sodium atoms, so we know their mass. They have a momentum. I can calculate a wavelength, a few hundredths of a nanometer. Now let's take a baseball, an object that we know the size and mass of, a macroscopic object. A macroscopic object like a baseball, 170 grams, set by the Major League Baseball Association, a standard baseball, thrown at 40 meters per second. That's a very good fastball. We can calculate, using the de Broglie relationship, the wavelength, but look at how small the number is. This is 10 to the minus 26 nanometers. We were already at nanometers, 10 to the minus 9. Now we've gone to 10 to the minus 26th of those. This is an incredibly small distance. It's so small, it's insignificant. And that's why you say if you take a macroscopic object, if I take this tennis ball and I throw it, I give it a velocity, I don't notice a wavelength. And you don't notice a wavelength because the wavelength is vanishingly small. In order for the wave-like properties of matter to manifest itself, the matter must be very tiny. If you have very, very tiny matter with very tiny momenta, then the wavelength creeps up into a region where you could actually detect it. So particle and wave nature of matter is going to be important for small particles, but not for macroscopic large particles. We don't even notice it. Particles, electrons, small atoms, have wave-like properties. Let's look at that in terms of a chem quiz. How many photons, they're going to behave like particles, should about stop that sodium atom at 80 Kelvin? The sodium atom impacted by the wavelength of light, behaving like a particle, behaving like a photon, about how many will stop that? About 1, about 100, about 10,000. Think about that and make your selection. Let's look at possible explanations for each answer. A, one particle will interact with one wave by the de Broglie relationship, so it'll be a one-to-one relationship. B, 100 photons reduce the temperature about 100 K. That's near zero, and the sodium atom should be about stopped. Or C, the sodium atom wavelength is about 1/10,000th the photon wavelength, so 10,000 photons are needed for an equal transfer of momentum. Think about those three explanations and make a selection. Matter has both wave and particle characteristics. We've seen the momentum and the wavelength are related by the de Broglie relationship, and we calculated it for several different objects. Now we're saying, well, a sodium atom is going to be traveling at about 300 meters per second. It's going to encounter photons of 600 nanometer wavelength. About how many photons have to strike those sodium atoms to get them to slow down and about stop? Well, if you look at this, here's the sodium atom traveling at 80 K. That's its temperature at about 300 meters per second. It has a wavelength, as we've seen, about 6/10 of a or 6/100 of a nanometer. Those photons of yellow light coming in at 600 nanometers. We can say, well, I want the momenta of these two systems to be equal. I want to transfer enough momenta from these waves to stop the particle. So the wave has a particle nature. It has a tiny little momentum. I need to transfer it to this larger momentum, and here comes the sodium atom, and I want to bap, 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 bap. Keep hitting it with photons until bap, 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 bap. That sodium atom about stops. And I can do that by just calculating the momenta of each, and as I do so, I see that the momenta are related by their wavelength, by the de Broglie relationship, and we can see the momenta of the photons are about 10,000 times smaller than the momenta of the sodium atoms. So what I need are about 10,000 photons to about stop a sodium atom. You can actually do this experiment. It's fabulous. This experimenters who did this were awarded a Nobel Prize for what's called laser cooling. You can take atoms and slow them down, the smallest, lowest temperatures ever achieved, by cooling things by traditional means, in refrigerators and by vacuum pumping, and then using this additional method, using lasers to trap the atoms and bounce photons off them till they virtually come to a stop. The lowest temperatures ever achieved by what's called laser cooling. The correct answer for our laser cooling experiment is C, about 10,000 yellow photons to stop that sodium atom. We're in the demo lab with Lonnie, and I've asked him to give us a demonstration of quantization of waves. Let's see what he can come up with. He's got a tube, and as he spins it, we get a tone. And a higher tone, and a higher tone, and a higher tone, and yet a higher tone. So 5 distinct tones rather than a continuous doop. So we see quantization of the wavelengths that fit in the length of that tube. Quantization of acoustic waves. Particles, especially tiny ones, have a wave-like property that we can resolve. And we saw that with electrons going through a crystal diffracting. Some particles of the wave hitting at some portions of the screen, some hitting at other portions of the screen, some portions of the screen forbidden to hit. As if the electrons come through, interfere with each other like waves, and are only allowed to hit certain points on the screen. It actually gets a little spookier than that. If you send the electrons through this experiment, one electron at a time, they still cannot hit certain parts of the screen. I think you can imagine, oh, electrons, a lot of them behaving like waves and interfering with each other. but the electrons, behaving like both particle and wave, when they go through that grating, they somehow know not to hit certain parts of the screen. It's a very, very, very spooky property of matter. And from here on in chemistry, we're going to talk about those very spooky quantum properties of matter. Let's start by looking at a classic experiment or a classic calculation, a particle in a box. You can imagine taking a particle that has a wave-like property and trapping it in a small region of space. When you trap it in a small region of space, you get wave-like properties occurring. And those wave-like properties are well defined when you trap the particle. Now, you trap the particle in space. Let's draw a picture of that. A wave-like particle trapped in space, I'll draw like this. I'll say a box of length L, and the particle has to be between here and here. It'll have a wave-like property, so I'll draw a wave-like expression on this box. Now, this wave-like expression I'll call the wave function of that particle. The wave function of that particle will give the designation psi. In this case, psi of x, because this is the x dimension in space. Now, we've already said that the intensity of the wave squared is going to give us an indication of the probability of finding the particle. So the probability, psi squared, gives us the probability of finding the particle. Clearly, in this case, the probability of finding the particle right in the middle of the box would be very high if this particle behaves like a wave. Well, how do I come up with these wave functions? Well, I can actually do some mathematics. I can say, write down the physics, the kinetic and the potential energy of the particle, and the boundaries that I'm putting on the particle. And when I do those things, I can solve the differential equation for the particle stuck in this tiny little box. It's behaving like a wave. There are those wave functions psi. These are how the wave functions psi must interact with each other if it's a particle to be stuck in this box. Now, we won't go through all the mathematics, but you can solve this. And when you solve this equation, you get an expression for psi that's not that hard to understand. And it looks like a wave function. There's a sine function, an oscillating sine wave. That you'll recognize from your high school mathematics. Psi of x is sine of x. The length of the box is in there, and another parameter, n, is in there. There's not just one solution to this expression. There's multiple solutions. All the integers n work and give you a solution to this equation. So that means there's not one wave function that works. There's several wave functions that work. You can have a ground state, the smallest value of n, but you can have what we call excited states. Higher values of n also give wave functions, and you can tell what happens. This value n is here in the sine expression. As that integer n gets larger, you'll get more waves appearing in your box. So these functions psi give us the probability when we square them of finding the particle at various locations in the box. We can also say, well, what's the energy of that particle? We can calculate the energy using our expression for the wave function and the probability squared. And we can say, well, I'll rank the energy. These particles increase in energy as n increases. The expression for the energy of the particle in terms of this quantum number, we're going to call it now n, go like the energy of the nth state, n squared, h squared, over 8m L squared. The length of the box, the quantum number, Planck's constant are all in there. So I can then plot out, well, the lowest energy state, n equal 1. We have no n equals 0 state. N equal 1 is where we start our counting. N equal 2, higher energy state. You'll see n goes in as the square. So higher n, higher energy state. N equal 3. We'll also calculate and catalog what we call the nodes, the areas of the box where there's 0 probability of finding the particle. 0 probability are the places where the wave function goes to 0. After you square 0, you still get 0, so the probability of finding the particle at these crossings is 0. And that's a strange characteristic of particles that behave like waves. There's portions of the box where the particle is forbidden to be. So this is interesting. I'll have two nodes, 1, 2, node A, area where the wave function goes to 0 in the high energy state, one node here and 0 nodes here. When the number of nodes increase, the energy state increases. That's a higher energy situation. So here's what I have. I have a wave. I'm bounding it on either side. And like you saw in the demonstration, when you have a wave-like property, you bound it on either side, only certain wavelengths can exist. So half a wavelength, one full wavelength, 1.5 wavelengths. I can't fit 1 1/3 wavelengths in this box, or 1/4 of a wavelength, because the particle has to go to 0 probability at the ends. So if I fix the ends of the box, I put boundaries on a wave, I naturally get what I call quantization. Not every wave can fit in these boxes. Only certain waves can fit in these boxes. And there's a gap. I go from here, n equal 1, all the way up to here, and I skip all those energies in between. I can only have this energy state for the box or this energy state for the box, and no energy states in between. The energy is quantized. And waves naturally do this. It's not unusual to see it. We can demonstrate it with audio waves. Audio, sound, is a wave-like property. And here's a tube of fixed length. So if I want waves to exist on this tube, only certain wavelengths will fit. I'll be able to fit, a full wave on this, a wave on this, a wave and a half on this. So only certain sounds will fit in this tube. That's an interesting characteristic. I can demonstrate a couple of the sounds that fit in this tube. We won't hear, when we figure the sounds that fit in this tube, we won't hear continuous sounds. We won't hear boo. Continuous wavelengths will have boo and boo, two individual wavelengths that fit in this box. Let's actually demonstrate that. I'll try to spin this and you guys can listen. There's one wave that fits. There's another wave that fits at higher frequency. Higher frequency, lower wavelength. And there's that low frequency, long wavelength. Two energy levels, and you can see energy. It takes me more energy to get to that high frequency than this low frequency. I wonder if I can get a higher one. I can even get a higher one. That's a beautiful acoustic example of waves and quantization. All you need to get quantization is take a wave and force it to exist in a certain area of space. If you fix the ends of a wave, you get quantization. If you take nothing else home from Chem 1, take home the fact that when you take a wave and you stick boundaries on it, you naturally get quantization, whether it's a matter wave, an electron stuck in a box, or an acoustic wave existing in this little primitive instrument. Matter has wave-like properties, and when waves are bounded, you get quantization. You get a particle in a box. If I have a particle that has wave-like properties and it's trapped in a box, we understand that it has different energy states. And how do I make a transition between one energy state and the next energy state? Well, I absorb energy. I absorb an amount of energy equal to the gap between those energy states. So let me ask you, which is true about the photon energy? I could absorb the energy in terms of photons, absorbed in each transition shown. So here's transition A and transition B. So a particle in a box length L, and a particle, same particle, bigger box. Now, I haven't drawn A and B to scale. The question is, which transition is bigger, has the larger energy transition? Is A bigger than B? Are they about the same? Or is A smaller than B? Think about that for a minute and make a selection. let's look at a possible explanation for each of the answers. A smaller box size means a larger spacing of the energy levels, so A is going to be bigger than B. Or for B, twice the box length means double the energy, so the transitions should be about equal. Or C, n equal 2 for an L-length box is equal to n equal 4 for a 2L box, but the ground state's lower. So 2L will have B larger than A. Think about those and make another selection. We're looking at identical particles trapped in two different boxes, one box twice the size of the other box. So if you look at the particles trapped in the boxes and you excite them, you say go from the n equal 1 ground state to the n equal 2 excited state, for instance, for the small box, what does that look like? Well, you could calculate the energies based on this expression, but you could also just look at the energy levels of both boxes. Here's n equal 1, for instance, for the smaller box, and n equal 2 for the smaller box. N equal 1 for the larger box here, and n equal 2 for the larger box. And here's where you notice something interesting. If n equal 2, and you put that into the expression, you get a 2 here and a 2L here. That actually energy level lines up with the n equal 1 case for the smaller box, because you'd have a 1 here and a 1 here. So you get cancellation in the 2 case for both the larger box and the n equal 1 case for the smaller box. Those energy levels turn out to be the same. And if you look at the n equal 4 case, that lines up in energy with the n equal 2 case for the smaller box. So what you have are a transition between 2 and 4 would give you equal energies, but a transition between 1 and 4 for the large box is bigger than 1 to 2 for the small box. So the correct answer here, A transition smaller than B transition. If you take a particle that behaves like a wave and you trap it, you put boundaries on it, you trap it in a box, it turns out it can only have certain energies. It's not like when you take a marble and you put it in a box and you shake the marble around. It can have any old kinetic energy it wants. It can be going fast, it can be going slow, it can be going at a continuous amounts of velocities in between. That's not true for a particle that behaves like a wave. Particles that behave like a wave can have only certain energies. The energies are quantized. Remember, wave plus boundaries gives you quantization. So I have some quantized levels written here, and quantization is the fundamental property that allows absorption and emission of light. Because if you're going to make the system go from one level to the next, you can't absorb just any old wavelength. You have to absorb the wavelength that actually fits, that gives you the exact amount of energy to go from low state to high energy state. All other energy levels and all other energies that the system experiences will be ignored, but energies that fit its energy map, energies that map onto this, will be absorbed or, conversely, emitted. So here's a wavelength, high energy wavelength, exposed to that system, but there's no spacing, energy spacing, equal to that energy. So that is transmitted. Here's a wavelength that exactly matches this high energy transition. That one will be absorbed. And when it's absorbed from the spectra, you see it's missing in the continuous band that's being exposed to the matter. That wavelength is absorbed. You'll get a dark area where that wavelength is absorbed because the system has an energy spacing that matches that frequency. And of course, atomic and molecular transitions work like this. You'll have some wavelengths that will pass right through, some wavelengths will be absorbed. It's like the Goldilocks principle of atomic absorption. Some wavelengths are too big, some are too little, some are just right. So you have another just right, that will be absorbed, and perhaps you'll find a third just right energy level that will be absorbed. So you get an absorption spectrum that says, oh, this blue, this yellow, and this red are removed from the continuous light that's hitting this object. Or you could have the light emit by the system. The system could emit the energy of the high wavelength, and then you'd have a single emission. It can't emit all wavelengths of light. Only certain wavelengths of light are emitted. And this is why things can have certain colors, because they'll emit certain wavelengths of light. Here, at this example, a blue wavelength, a lower energy green wavelength, and a still lower energy red wavelength. Absorption and emission of light by objects that are bounded, say electrons, in a box, have certain energy levels, therefore certain absorption and emission frequencies. Matter absorbs or emits light based on its fine electronic structure. That is, you have electrons behaving like waves, they're bounded in the matter, so they have only certain energy levels that can exist and only certain transitions that are allowed to be absorbed or emitted by photons stimulating that matter. Now, let's take this. Let's say a certain piece of matter has this energy level scheme that's shown here, and it has an emission spectrum. Which of these three emission lines arises from the transition of high energy to low energy, 3 to 1 emission in this system? Is that A, B, or C? Think about that for a second and make a selection. Let's look at possible explanations for each answer. A is the highest frequency transition, so it also has the highest energy, and 3 to 1 is the largest energy spacing. Or B is in the middle, and transition 3 to 1 has an energy level in the middle, so there's a similarity between the energy level spacings and the spectrum itself. Or C is the highest wavelength, and therefore highest energy transition, and 3 to 1 is the largest energy spacing. Think about those three options and make a selection. We're trying to get from the energy level spacings in some matter to the actual emission spectrum that we'd observe. So if you look at the possible energy transitions, a transition between level 3 and 2 is possible. That would be the lowest energy of the possible. That's the smallest spacing here, so that's the smallest energy. So on a frequency plot, it would be the lowest frequency or highest wavelength. If you look at the transition from 2 to 1, also possible, that's a bigger energy spacing, higher frequency. The other transition from 3 to 1 is the highest possible for this system. So 3 to 1 would give you a line at A here. The highest energy transition is the highest frequency, is the correct answer. Let's look at an energy level spectrum, so some energy that's emitted or absorbed from a system, and try to predict what the electronic structure, what the spacings are in that actual system of matter. So the reverse of what we did last time. So to which energy level scheme, A, B, or C, does this emission spectrum correspond? Think about that for a minute and make a selection. Some possible explanations for each answer. A, when you flip an energy level diagram 90 degrees, that's a good way to arrive at what the spectrum looks like. Or B, 2 small transitions give the same low energy line, and 3 unique high energy transitions give the higher lines. Or C, there are 3 large energy spacings and 1 small one, and the spectrum has 3 high and 1 low energy line. Think about those 3 possible explanations and make another selection. let's look at the relationship between emission spectra and energy level spacing in the matter. So if you have a energy level spacing that looks like A, what would the emission spectrum look like? Well, you have to look at every possible transition in the system. And here you can see 3 high energy level transitions. Those would give you high frequency lines. And 3 low. You could have this tiny transition, this tiny transition, and this tiny transition. These 2 of equal energy. So they're degenerate. They would fall right on top of each other and give you only 1 line, even though there's 2 transitions. But the 2 transitions have the same energy, so we can't resolve them in terms of energy. So you'd get just 2 lines, one for this transition and one corresponding to both of these transitions. So that doesn't look like the right answer. If we look at B, we have 1, 2, 3, 4 transitions, but these middle 2 are the same energy. They would fall right on top of each other. So you'd have a very high energy level, a medium and a medium at the same energy, and a low in your high band. That's a total of 3 from these 4 transitions, since 2 are exactly the same. And then 2 tiny low energy transitions, but again, they are of equal energy. So that would give you 1 line. That looks like the spectrum we've seen. And if you look at C, that of course isn't anything like what we see. You have 1 large energy transition, and then 2 energy transitions in the intermediate range, but this one, this pair, and this pair are of equal energy, so they'd give you only 1 line. So this pair gives you 1 line, this pair gives you 1 line, 2 intermediate lines, and then a small energy transition. So you see how you can analyze a energy level diagram and go to a spectrum and kind of backwards and forwards. That's why a spectrum is valuable. It tells you by inference something about the actual matter. And remember, you can't look at tiny little matter in your microscope. You have to bathe it with this electromagnetic radiation, see what it absorbs and emits, and by thinking about what it absorbs and emits, reconstruct what its energy level diagram might be, what its electronic structure might be. So here, the correct answer is B. Lonnie's in the demo lab preparing to demonstrate laser-induced fluorescence. Fluorescence occurs when high-energy photons are absorbed and lower-energy photons are emitted. Lonnie will start with an ultraviolet laser that's higher energy than the visible region. As the ultraviolet laser passes through this blue solution, ultraviolet photons are absorbed and blue photons are emitted. Here, ultraviolet photons are absorbed and photons in the green are emitted. Here, ultraviolet photons are absorbed while photons in the yellow are emitted. And ultraviolet photons stimulate the emission of photons in the red region in the final solution. Now let's try that same experiment with a lower energy laser. This is blue in the visible region. So in order for fluorescence to occur, we have to absorb a high energy photon and emit a lower energy. So here, blue laser is transmitted through the blue solution, but blue photons are absorbed here and photons in the green are emitted. Here, blue photons stimulate the emission of photons in the yellow, and in the final solution, photons in the blue region stimulate the emission of photons in the red region. One final laser, a green laser, so even lower in energy of photons, lower than ultraviolet and blue photons. So the green laser, insufficient to stimulate emission in the blue, and the green laser transmitted through the green solution, and the green laser stimulating emission of yellow photons from this solution, and the green laser stimulating emission of photons in the red region from the final solution. So the laser-induced fluorescence demonstrated by lasers and a colored solution.